In this unit, we are going to extend our idea of optimization, or approaches for finding optimum values of a function, but we're going to add something new. We're going to add explicitly a constraint, or a limitation, as a synonym for this, on what we can choose for our inputs. And what that's going to do is, as we saw in earlier examples, it's going to define a domain that's restricted, and so it's going to affect how we search for our maxima and minima. And what's interesting is there's a nice connection here back to the gradient, and perhaps a surprising connection back to the gradient. To be more specific, let's talk about the kinds of problems we might be analyzing with the approaches in this unit. For example, show that a square of maximum area, so we're trying to maximize the area as our objective, and that has a given perimeter, and that is fixed. Or if you like, that would be a constraint. I can't just choose any rectangle I like. I can't make it super large because I can only have a certain perimeter to work within. How that works in the mathematics is that we have a function, a of xy, often called our objective function. That's the objective we're trying to maximize or minimize. And then we have a constraint, which also has a nice form to it. And if we have our rectangular example here, x and y, we can very easily derive that the area would be the product of those two values, and the constraint would be the perimeter, which is two y's and two x's have to add up to equal some specific value p. And what we're trying to do now is come up with a system for combining these two in a direct way without actually solving for y and putting it in the other equation. We're going to see if there's something a little more general we can do. As another example, find the point on the sphere x squared plus y squared plus z squared equals 4 that is closest to the point 335. So just in terms of imagining the shape or the problem here, this is a sphere, radius 2, centered at the origin. There's no shifts in the x, y, and z's. So we have a sphere, and there's going to be some point 335 that's well outside of the sphere. And so we want to find the point on the sphere that's closest. And if that's what we're looking for, then what we would want to minimize is the distance as a function of the point on the sphere. So x, y, z is a point on the sphere. And depending on which point we choose, the distance to 335 would be the distance from my point to 3 and x, the distance from my points y to 3 and y, and z to the 5 value for z, square them square root to get a distance. However, we can't just pick, if I want to minimize this, I would just pick x equals 3, y equals 3, z equals 5, I'd get 0 distance. We have a constraint that we can't work around, and that's that the x, y, z that we pick must satisfy the sphere equation up here. And these kinds of optimization problems with a constraint are incredibly common, and so it behooves us to look into them a little bit further and see what kind of mathematical structures we can find.